Today we're going to talk about the dot product, where it comes from, and its geometric meaning. Okay, so let's begin by talking about what we're going to go over today. First off, we're going to derive the formula that's used to compute the dot product of two functions, and we're going to talk about what it is, what it represents. Then we'll go through an example of computing the dot product of two vectors, and after that we'll discuss the geometric meaning of those two vectors, again using the formula that we derive for the dot product. Alrighty, so what the dot product is it's another name for the scalar product of two vectors. Okay, now what does that mean? Well, that's what we're going to go over here. So imagine you have two vectors, u and v, right? And they're positioned at an angle away from each other, like we have in the diagram up here. It can be said that if we subtract those two vectors, that the resulting vector will be the connecting endpoints right here, where we take the initial point of the vector v and connect it with the terminal point of the vector u. That's what happens when we subtract vectors. Alrighty. And this is going to be kind of the trick here, right? What we're going to do is we're going to use the cosine law to come up with a relationship between these three vectors that we have in the diagram here, so that we can try and come up with some sort of geometric meaning for what's going on here with respect to theta. And then once we have that geometric definition, we can come up with some formula for the scalar dot product. Okay. Now, we're also going to need to recall that the norm of a vector, or a way to compute the magnitude of the vector in n dimensions, is found by the root of the square of the root of the sum of the squares, okay, of each component of that vector. All right, so if we have a vector in two components, you square each component individually, add them together, take the square root, and that will give you the magnitude of the vector. This is just the Pythagorean theorem, and that can be quite easily derived as well. If you wanted to check that this formula I have up on the whiteboard is true for 3 dimensions, then just draw a triangle on a piece of paper and extend it into 3 dimensions to prove it using the Pythagorean theorem. Okay. When we use these two ideas, what we're going to end up with here, replacing the pieces in the cosine law, is the magnitude of u minus v squared has got to be equal to the magnitude of the vector u squared plus the magnitude of the vector v squared minus 2 times the magnitude of the vector u times the magnitude of the vector v cosine of the angle theta, which is displayed in the diagram above. Alrighty. Now, if vectors u and v have components u1, u2, u3, and v1, v2, v3, then we can rewrite the magnitude of the vector u minus v as the sum of the squares of the components, right? And if it's normally under a square root when we have the magnitude and we square it, then the square root and the square cancel each other out, right? So we'll have u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. And then, of course, that's got to be equal to the stuff on the right side here. So I've got the magnitude of the vector u. Again, that's equal to the square root of the sum of the components squared. And if I square that, then I just have the sum of the components squared, right? So u1 squared plus u2 squared plus u3 squared. And likewise for the vector, the magnitude of the vector v being squared, I'll get v1 squared plus v2 squared plus v3 squared. And then I'm just going to leave this last part alone. So negative 2 times the magnitude of the vector u times the magnitude of the vector v cosine of theta. Alrighty, now when I manipulate the left-hand side a little bit here, what I'm going to end up with is I'm going to end up with u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared plus u3 squared minus 2u3 v3 plus v3 squared. And that's all equal to the same stuff on the right-hand side of the equal sign. And it can be shown that all of those terms, except for the negative 2 magnitude of u times the magnitude of v cosine of theta, will cancel on the right-hand side with the left. so that we're just left with negative 2u1v1 minus 2u2v2 minus 2u3v3 on the left-hand side. I can factor a negative 2 out of everything here to be left with this definition right here for the scalar dot product. Alrighty. Now the right-hand side of the equal sign here, that's going to represent the geometric version of the dot product, and we'll discuss more of that later on here. But let's let the dot product of u and v, which we write as u dot v, as I shown above here, as u1v1 plus u2v2 plus u3v3. And then let's also make note that the dot product is also equal to the magnitude of u times the magnitude of v times the cosine of the angle theta. Alrighty. Now, how is that useful? Given that geometric definition for the dot product, well, it can be used to help us find that angle between two vectors, right? Because we know how to compute the magnitude of two vectors. We know how to multiply. And if we have this scalar definition for the dot product, then we can compute the dot product of two vectors quite easily as well. Then if we take the inverse cosine in radians, then that should give us our answer in radians. Okay. Alrighty, so now what we'll do is we'll work through an example of computing the dot product of two vectors, and we'll discuss the geometric meaning behind that dot product as well. So imagine that given this definition for the dot product, we have the vector u in 3 dimensions being the vector 1, 3, 5, and the vector v in 3 dimensions being the vector 2, 4, 6. Okay, if I take the dot product and use the scalar dot product definition on the left-hand side of the equal sign, I'll be left with u dot v is equal to 1 times 2 plus 3 times 4 plus 5 times 6. So I'm just multiplying each of the components for the two vectors that are being dotted together and adding them all together. This is going to give me 44 when I do this, right? 2 plus 12 is 14, and 14 plus 30 is 44. And now as for the geometric meaning of this dot product that we've just computed here, let's go ahead and find the angle of let's go ahead and find the angle theta, which is between the two vectors, by using that dot product and dividing it by the product of the magnitudes of the vectors. So, all right, let's first compute the magnitude of each vector individually. The magnitude of the vector u is just going to be equal to the square root of the square root of the components squared, sum together, right? So that's going to give us 1 squared plus 3 squared plus 5 squared all under a square root. That's 1 plus 9 is 10 plus 25 is 35. So the magnitude of the vector u is the square root of 35. As for the vector v, what we'll do is we'll take 2 and we'll square it. We'll add it to 4 squared and then add it to 6 squared and take the square root. That'll be 4 plus 16 is 20. 20 plus 36 is 56. Now, if I put these all together, and I have this in a little bit of a simplified form, what we would end up with is 44 over the square root of 1960. And then, of course, 1960, if you simplify that a little bit, that can be written as 14 times the square root of 10. And then we've got a 44 on the top and a 14 on the bottom. That's the same as 22 over 7. And you'll just rationalize the denominator by multiplying by root 10 on the top and the bottom. And eventually, after a little bit of more manipulation after that, you'll end up at this formula for the arc cosine. Obviously, just typing the other piece into your calculator should give you the exact same answer. But what we're getting is that we have approximately an angle of 6.35 degrees between the two vectors that we've been given here. Alrighty. Well, let me know if you have any questions. I've got my email and my phone number up on the whiteboard. But yeah, hope you have a great one.